now that everyone's had a big carbohydrate-laden lunch, which will guarantee you will fall asleep in about 20 minutes, we can leap into a complicated topic that will be hard to follow. Actually, it won't be that. What this talk is messaging. I'm going to look at two different messaging systems. I'm going to look at Rabbit and I'm going to look at Zero. The two of them are, sometimes you use one, sometimes you use the other. Neither is clearly better. Which is to say, it depends on the context. I'll talk about AMQP in a minute, but Rabbit is based on it's based on a protocol called AMQP that's widely supported by enterprise-level messaging systems. So what that means is that if you need to integrate into an enterprise-level messaging system, Rabbit is your choice. ZeroMQ is based on nothing. It's its own thing. On the other hand, ZeroMQ is much easier to use than any AMQP messaging system. So ZeroMQ is your choice if you are building an entire system of your own that doesn't have to integrate with anything in particular, and you want the simplest possible programming model. So as to neither one is appropriate or inappropriate, you could use them interchangeably in the sense that if all that you're doing is messaging internally inside your own app, it doesn't matter which one you use. But when you have to go to an outside app, you have to go to an enterprise messaging system, Rabbit is your only choice. And if you know it's a fact that you're never going to have to go to an enterprise messaging system, I would go with Zero because it's easier to program. So those are that's why we need to talk about both of those, that both of them have their applications. On the other hand, they're both messaging systems, which is to say there's a lot of commonality between them and certainly a lot of common architecture between them and common concepts. So I'm going to start by talking about conceptual things. I should also say I've got these slides up on my website right now. They'll also be on the conference website, but I just uploaded them this morning, so there's a fresh version up on my website. You can go to the slides directory. The one thing that you won't see, but I'll get you anywhere off for it in a moment, is a little demo of what everything is, and you get a link to that on the URL. So let's talk about messaging for a minute. The concept of the notion of messaging is that you are sending a payload across the wire between a producer and a consumer. So we have a message. The message has in it a payload of some sort. Now what that payload is pretty much arbitrary. Is that it could be binary, it could be big, it could be small, it could be text, it could be JSON. If you're going to work in a microservice environment, which is where I'm using messaging most heavily nowadays, my payload is always JSON. It's always human readable ASCII. And the reason for that is that in a microservice environment, but this is the case in almost any environment where you'll see messaging, the consumers, the things that are handling the messages, are in a sense an unknown quantity. And in a microservice world, each service will be a consumer. And the servers could be written in various languages. They could be written in varying operating environments. They could be running on different operating systems, running on different machines. And if you start sending binary data around, it's a world of hurt. Is that you don't know whether it's big endian or little endian or, what's the precision, et cetera, et cetera, et cetera. JSON is completely implementation and context independent. It's all ASCII. It also has the advantage of being human readable, so it's easy to log, it's easy to see what's going on inside the system as it moves around. So more and more I have been avoiding having binary payloads. It's just isn't worth it. If you were sending massive amounts of data around, I don't know that messaging is the best way to do that anyway. Right? In other words, that's where you would fall back onto a binary payload. But to be honest, I think you would be better off putting that massive amount of data in some other place and sending its address around and sending the data around in that kind of situation. So generally speaking, the payload is going to be text. It's going to be something that's human readable. None of these systems, though, require that. The payload can be any string of bytes you decide to send. I should also say string of bytes is that all of the messaging systems are ASCII. They don't mess with Unicode. Unicode is another world of hurt. It's just too hard to interpret. So UTF-8 and yada, yada, yada. Anytime there's a string in a messaging system, it is an ASCII string, 8 bits per character. So again, the payload is arbitrary. So if you want to send encoded Unicode across this payload, go for it. Right? But in terms of the messages themselves, I would recommend avoiding that. It's just stick to ASCII. Now, the message then travels from the producer to consumers. In the case of Rabbit, through a broker. In the case of ZeroMQ, which we'll get into a minute, not. Zero is a brokerless system. Rabbit is a broker-based system. Now, by broker, I mean it is actually a server, not just in the sense of a program, but also in the sense of a machine, usually. Now, for testing purposes, it doesn't have to, because the broker could be running on this. The broker service could be running on the same machine as the code that you're building and testing. But in practice, the broker is going to be one or more machines living in a cluster in a data center someplace. So everything in Rabbit is done through the broker, so let's start there. Now, there are a couple of advantages to a broker architecture. One of them is that the brokers, since they are running on their own machines, can be maintained by a bunch of professionals whose job it is to maintain stuff. In other words, they can go inside a data center where there are people whose job it is to keep them live. The second issue with the broker is it's replicable in the sense that you can have a cluster of brokers. So you can have a cluster of several machines that act as a single broker. Now, the downside of that, as compared to a point-to-point kind of system, though, is that it is a single point of failure, either physically or logically, inside the system. So in most small messaging setups, the broker is just one service running on one machine. And if that machine goes down, you're host. And implementing a clustered environment is possible, but it's hard. Is that somebody's got to study to do it. They've got to be certified as an engineer that knows how to do this kind of stuff. And it's not something you want to do unless you have an enterprise requirement to do that. So brokers then are kind of a mixed bag. The third thing about brokering that I'll talk about a little bit more when we get to the ZeroMQ part of the talk is addressing. Now, if you think about it, the broker is a machine by itself. So these two connections on the two sides of it have to have well-known addresses, TCP addresses at well-known ports. These guys don't, because these guys connect to the broker from the outside. And as many people as possible can connect, as many services or producers and consumers as possible can connect. And nobody needs to know what their addresses are. And that's actually a good thing. Right, so the basic concept is this is called a bind and this is called a connect, right? And you bind to a specific physical address. And then you can connect to that address. Ideally, in any kind of messaging topology, you want to have as few binds as possible, because that makes things inflexible when you have binds. You have to know what the address of it is in order to bind to it. It's better to have connects. So brokering systems, at least messaging systems where you have a thing in the middle, is helpful because it concentrates all of the known physical addresses in one place. And the vast majority of the system doesn't have to be at known addresses, which makes it much more flexible. Is everyone following what I'm saying here? In other words, if the consumer were a service, and I wanted to put a new service on, I can put the new service on and it can just connect to the broker. And the producer doesn't need to know that I put a new service on because it doesn't need to know its address. Right? If the service was bound to an address, I'm in deep trouble because now every time I put on a new server, I have to somehow tell that to the producer who then is going to have to physically bind to it, and that's not really a good situation. You want to use messaging for a bunch of reasons. It's easy to put new requirements in the system because the handlers of the messages can be added very easily without impacting existing handlers. So in the microservice world, for example, where you're talking about a microservice that's doing exactly one thing, you bring a new service online that didn't used to exist before, the existing services don't even know that that's happened, they don't care. So when a new requirement comes along that needs new services in order to implement that requirement, you can just put the new service in place and you don't have to touch any of the existing code. It's painless with respect to scalability, and you can scale hot in the sense that I can throw more servers onto this system and nobody cares. It's just suddenly the load is distributed between multiple servers when before it was not. Well-done messaging systems require almost no load balancing. Is that the messaging itself does the load balancing for you. You can put new services online without having to bring down anything, and that's a good thing. It's easy to do background processing using messaging, and it's, in fact, Zero, not so much Rabbit because it's a little higher overhead, but Zero is very, very low overhead to use in an in-process kind of situation. So a service that's handling messages in ZeroMQ could actually be an object inside your program that's using messaging to talk to other objects inside the program. Now, the advantage of that is that there are a whole bunch of asynchronous design patterns built around messaging, which are vastly easier to keep track of than messing around with semaphores and stuff. Because nobody understands how low-level thread safety works. Nobody does. And, well, I do, but let's say that probably 5% of the people that use threading actually understand what the hell they're doing. And the stuff breaks all the time. If you go to a message-based strategy for multiple threading, where you have several services running on independent threads, talking to each other across a messaging bus, that solves 99% of the synchronization problems associated with multiple threads. And it does it in a way that's very simple to code. So messaging is actually a great solution in process for situations where you're going to have multiple threads, and particularly if you're doing background processing. It's good for distributed development because the message handlers could be anywhere. In the case of ZeroMQ, they can be in process, they can be on the same machine but in a different process, they can be on a different machine. You don't care. So what that means is that you can test all on one machine, you can develop all on one machine, but when it comes time to deploy, you distribute your application just by copying things to different machines, and you tweak the addresses. The TCP addresses, instead of being localhost, become something else, and that's the only change you have to make, and everything continues to work. So it's really easy to do development in this kind of environment. It supports polyglot applications in the sense that you can write all of your services in different languages if you want to. They don't care, as long as you're passing things around as JSON rather than as binary. So, and you want to do that, really. It's in the microservice world, it's kind of encouraged within limits. Right? You don't want to use every language you can possibly think of, but there are a lot of systems I know of that are part PHP, and they're part Scala, and they're part Java, and they're part C#, and that works just fine. So because of that, you can get very real independence between the modules because they don't have to be tied to each other through any dependency except to the messaging system. And that's obviously a good thing from a maintenance point of view. They're also great way, messaging is a great way to share information. So a lot of times, if you see old applications, people would share information through the database. One server would write to the database, another would read. You'd store session information in the database, for example. Messaging is a much better way to do that, to pass that information around. Database is very inefficient, and it's another single point of failure. So it makes development go faster, it improves the flexibility of the system. It makes it easier to develop, right, is that your development goes faster. It's really important. Rabbit itself is an open source system, which is not, it's written in Erlang, which is kind of a weird choice, though. Erlang is one of those languages that nobody is interested in outside of the academic community. Erlang is a purely functional programming language. Erlang has exactly one reasonable application to write in the language, and that's a messaging system. So the fact that in other words, Erlang, the one thing that a pure functional programming language gives you is thread safety. It makes it really easy to write heavily multi-threaded applications without having to worry about all of the problems that we usually ascribe to that. Messaging brokers are very heavily multi-threaded. So Erlang is actually a pretty good choice, except there's nobody in the world who understands it except the people that work on Rabbit. So practically speaking, the only downside is that we have to install the Erlang VM in order to run Rabbit, but that's done automatically when you install Rabbit, so it's not a big deal. It's polyglot in the sense that there are a gazillion bindings into Rabbit. Just about any language that you can imagine can talk to Rabbit, from JavaScript to C#. And it does use a standard protocol. It's built on AMQP. We'll talk about that in a second. There it is. So AMQP is a binary wire protocol. It's very efficient. It was created by people who were actually doing messaging. But I'll say that as a side here, it's people in the enterprise doing messaging. So it's kind of geared towards enterprise applications. It is interoperable, it's scalable, all of this usual goodness and light stuff. Oops. The one thing I will say about AMQP that I don't like, though, is that AMQP is built on a notion of guaranteeing as much as possible. The enterprise guys are really into guarantees. And AMQP allows for two very hard things. It allows for durability, which is to say that the message will continue to exist even if servers in the system crash while the message is progressing through the system. And it allows for guaranteed delivery in the sense that once a message is put onto the system, you are guaranteed that it will be delivered to somebody at the other end eventually. Now, those things are extremely hard to get right. In fact, I would argue that nobody has got guaranteed delivery to the point where it's actually guaranteed. There is no way to guarantee that every combination of servers crashing in inopportune times is going to be recoverable. It's just not going to happen. It's a dream. So there's a lot of complexity in AMQP that has to do with these guarantees. And it turns out that you don't need those guarantees for the vast majority of applications that use messaging. And so Zero, at the other extreme, gives you none of them. The only guarantee that Zero gives you is if you send a message in multiple parts, you'll either get all of the parts or none of them. Guarantees atomicity. But it doesn't guarantee anything about the message arriving. So if that's important, you have to do something in the code to make sure that it's arrived. You have to acknowledge the fact that you've received the message, which is not a big deal, to be honest. And it simplifies the messaging protocol so much that it's really worth, I think, a little bit of extra effort on the part of the program. Now, there are a couple of metaphors with respect to messaging that work across all systems, again, whether or not there's a broker present. So let's talk about them. First metaphor is the publish-subscribe metaphor, which we're all familiar with at some level. The basic idea is that you have a publisher who publishes things on a certain topic. And when the publisher publishes that thing on the topic, the publisher talks to the broker, but nobody else. The broker talks to the subscribers. But notice that only two of those guys got a newspaper down there. In other words, if you don't subscribe to the topic, you don't get the message. So the basic idea of publish-subscribe is that only people interested in certain topics get messages. And it's up to the subscriber to express its interest in the topic in order to be informed when something is published to that topic. Now, there's usually wildcard mechanisms here. So, for example, there might be a logging subtopic. You might have a service topic with a logging subtopic. And all of the services would subscribe to the service topic. But then a logger might subscribe to the service's logging topic. Now, does everyone see what I'm saying? But there might be a logger that subscribes to the equivalent of star.log. I want to hear logging for every service, regardless of what it is. Right? So there's a certain amount of wildcardness that's useful with respect to defining how the topics work. But this is a topic-based system. This is based on, the publisher doesn't know how many subscribers there are. The subscribers don't really know who the publisher is. The publisher could tell him. You could put into your payload some kind of return address or some sort of indication about who's doing the publishing. But generally, the subscribers are just interested in being notified that something has happened. Now, the other metaphor that you see a lot is the notion of a queue, which is a push-pull metaphor. Is that somebody pushes something into the queue, somebody else pulls something out of the queue. So I'll put some message into the broker, I'll pull it out into the consumer. Now, the consumer could send it back, but that's another push-pull. Right? So there'd be two push-pull relationships there. And it could send back a different message, as I've tried to indicate here in green, but it could also send back the same message. Right? The message is after all just a bunch of arbitrary stuff in the payload. All right, so what else here? Now, this can happen, several sorts of things can play out, right? We can have these complicated systems where the message goes to a consumer, and the consumer then sends the message to a different consumer somewhere else, and then that consumer sends it to another consumer, and this can bounce around in a very complicated way. But these are all just push-pull through queues. They might be the same queue, they might be different queues. So the thing about a queue is that you need to know about the queue in order to push to it or to pull from it. Is everyone following what I'm saying? So you have more information about routing here than you would have in a pub-sub kind of situation. Now, of course, there's also various consumers can hook up to the same queue. In other words, there's no requirement that there be a one-to-one on a queue. You could have both multiple producers and multiple consumers on And the way the messages go can vary. So for example, a message can go up to the broker and go to one consumer, or it can round robin from one consumer to multiple consumers. Or you can set that up in a broadcast kind of mode where it splits up and you get a copy on all of the consumers. So that's something that's under your control, is you can control how the queue works with respect to how it distributes messages off the other side. Right? So if you had a service, for example, that was handling a request coming into a microservice cluster for some reason, you could arrange for that service to round robin, or that request rather, to round robin across several services. In other words, 4 services could hook up to the same queue, and you could push into that queue and then one of them would pull out. Or you could have a service that goes into the queue and they all pull out in parallel. Right? Is that they're both useful in different kinds of contexts. Now, in Rabbit, and this is just in Rabbit, they have a kind of odd way of implementing this stuff, which is different than most of the messaging systems that I've seen. In that, from the outside, you just have producers and consumers, and that's all that you're typically thinking about. There are queues inside the broker. This square here is the broker. There are queues, and the consumers will connect to the queue in the normal way. However, the producers don't actually talk directly to the queues. They talk to something called an exchange. And the exchanges talk to the queues. So the exchanges can arrange for very complicated routing arrangements inside the broker that are not going to be visible from the outside. And it turns out that Rabbit, at least, doesn't distinguish really between a queue and a pub-sub kind of arrangement. Is that the only real difference has to do with the routing topology that you use. And I will look at that in depth in a second. So the main thing, though, is to think in terms of exchanges and queues being separate. And again, I'll give you more examples of that in a second. So you get a lot of decoupling here because of this arrangement. And that's good. You get logical decoupling in that the producer and consumer are really unaware with each other. They know about the broker, but they don't really know about each other. So that's good because the dependency relationships are all going in the correct direction. They're all going into the broker. There's physical decoupling in the sense they can be in different locations. Interestingly, you can also have temporal decoupling. Oops. In the sense that the message arrives at some time in the future. And sometimes you want to delay message transmission for deliberately, for some reason. Temporal decoupling sometimes can be an annoyance, though, right? As you send the message and it takes a while to arrive wherever it's going to arrive. That's not necessarily a good thing. Queues and exchanges, on the other hand, have their own properties, some of which are good and some are not. They're passive in the sense that you can check and see. It's just a thing that's sitting there, right? It's a service, and you can ping it, and you can see if it exists or not. And the queue isn't really doing anything until you stimulate it. They're durable, which is to say they continue to exist even if the broker comes down and back up again. Which is important, of course, because you're connecting to a queue, not to a specific broker. If a specific broker crashes, you still need to be able to send things to a queue when the broker comes back up again. They're exclusive in the sense that you can only one consumer can connect to it at a time if you set things up that way. They don't have to be set up that way. They can also be set up in a kind of auto-delete mode where the queue can disappear automatically if there aren't any consumers on it at all, which is occasionally happening. All right, is everyone with me here? Now, with Rabbit, when we talk about Zero, we're going to look at a bunch of code. When we talk about Rabbit, I'm not going to look at much code. I'll look at a little bit, but not much. Because with Rabbit, the coding is easy. Is that if you go onto the Rabbit website, there's a gazillion examples of them. And a good tutorial that takes you through from the simple to the complicated. What's hard to learn in Rabbit is the messaging topology. Is how to set up the queues and the exchanges so that they do what you need to do. So I want to focus on topology for the next few minutes. And if we have time, I'll go on to some code, but I want to just focus on topology. So I'm going to do that using a simulator. This particular simulator is available online. I've given you the URL for you to clone it if you want to. It's just like GitHub. I've also installed a version on my own website, so if you want to just play with it, the easiest way to do it is to just log on to my website. I'll show you the URL in a second. But basically, you just download this thing and build it and you're done. It's written in JavaScript, so it just runs. It's not a big deal. It's running under Node. So unless you have Node installed on your system, it's not going to run on your system. My version is here. So if you want to download it from that URL, or not download it, but use it on that URL, that's fine. So let me move over to the let's see how I'm going to do this. I'm going to mirror my display as well. So if it won't fit on your display, I'll do this. All right, now, this little simulator was written by the guys that wrote Rabbit. And they wrote it for exactly the situation we're in now, so that they could give talks at conferences about Rabbit and talk about topology. It is good for nothing else. This is not an administration tool. All right? And it's actually kind of annoying to use even when you're demonstrating topology. There's no way to erase anything. There's no undo or way to go backwards. So if I make a mistake while I'm up here, the only option I have is to reload the page, which is going to zero out everything. So I'm trying to be as careful as possible if I make mistakes here. Now, let's look at a couple of basic systems. I'm going to say all the topologies that I am about to show you are in the notes also, so that you can see the diagrams in the notes. You won't lose it just because I'm working on it. You start off with a producer. Everybody's got to have a producer. It's given a generic name to that producer. We can change it over here. I'm not going to bother. It's given a generic name to that producer. You need a consumer, obviously, but then you need to connect them somehow. So there's lots of ways that you can connect them. In order to connect them, you have to have an exchange, at least one exchange. And you have to have queues, at least one queue, because consumers connect to queues. Consumers cannot connect to exchanges. Now, if we look at the exchanges here, there are a couple of I'm going to be annoyed if it doesn't. It was working. I just tried it 10 seconds ago. It was working, so I don't believe it. It's not working. There. The queue, the exchange itself has properties associated with it. And in particular, it's got a name. But it has 3 different modes of operation. In a direct mode queue, the way that works is that you can talk to a specific consumer. A specific producer can talk to a specific consumer across a specific route.
Private.
It's effectively a private. It's effectively a private key, yeah. In fan-out mode, things that are sent to the exchange will fan out to all of the queues. In topic mode, it's actually going to look at routing in order to do this, so it's going to work more like a pub sub thing. I'll do that one next. Let's just do a fan-out one now because that's the more interesting of them. So I can take my producer and hook it up to an exchange. And then I can take my queue and hook it up to the same exchange, take my consumer and hook it up to the queue. Right? Now, if I produce a message here, any kind of message, the payload could be anything. I'm not going to worry about routing keys because that's a thing that only routing exchanges care about. And I send the message. It just goes to the exchange and ends up at the consumer, as you would expect. And you can send several messages and away they go. Now, things get interesting when I add another queue. Now when I send messages, it's in fan-out mode, so it goes to all the queues. When you start hooking up multiple consumers, then you start getting interesting behavior also. What was that? Well, a bunch of messages landed in this queue, right? Is everyone following how this is working? So we have durable messages. So they're sitting there in the queue waiting for somebody to connect. Right? If we have multiple consumers, things also behave in interesting ways. So here I've got multiple consumers on the same queue, and I'll send a bunch of messages. And look what happens when they hit that bottom exchange. They're round robining. Okay, so you can't have a fan-out queue, but you could have a fan-out exchange that goes to queues, each of which has only one consumer on it. If you went around robin, you round robin at the queue level. So everyone's seeing how this is going. So this is effectively a push-pull model, right? Is that you push to the queue, and then you push to the queue through an exchange. You pull from the queue simply by knowing how to connect to it. And requests are going to come out of the queue in a round-robin kind of way. Now, this is typically the way that you would make a request in a microservice world. One of the things that's nice about it is that, let's say my load is starting to get heavy. All I really need to do to handle that problem is put a new service on the system, and all of a sudden I've distributed my load among 3 services instead of 2 services. And I can do that very dynamically as the system is running. So we can have a very dynamic load balancing situation here if we can monitor messaging traffic. Is everyone following what I'm saying? I'll look at how we can monitor in a moment. But the point is that if messaging traffic, if we know what the traffic is like, if we have some way of measuring the load on a given server, and we notice that the load is coming from another threshold, it comes above some threshold, all we have to do is pop on a couple more services and we're done. And when the load goes below another threshold, we can shut down some of those services so that we won't be using compute time. This is an almost perfect environment for our cloud-based system, because we can be rolling up VMs in Amazon's space, for example, on an as-needed basis. When the load gets high, we'll spin up a new VM that will just automatically launch a service that connects to the queue. When the load goes down, we shut the VM down. And it's for modern kind of cloud-based computing systems, this is a spectacularly useful way to work.
How long do they persist for?
It persists as long as the machine is running, right? So the messages are durable, which in practice means they're stored in a disk someplace, right? And if the Rabbit supports clustering, it supports a shared database in which you can store the messages. But it's a hard problem. That's a hard problem. On the other hand, for a lot of web services, durability is not a big deal. If I make a request on a web page and it goes into a queue-based system and the system crashes, who cares? Right? See what I'm saying? The guy who's using the web application doesn't really care about that usually. If they do care about it, you have to set up things, obviously, so that it's going to be more fault tolerant than that. But if it was modifying a database, and if it was a financial transaction, for example, then you obviously have to care about it. But Zero doesn't give you durability; it doesn't guarantee durability. But it was built for financial transactions. It was built by bank. So it's just a matter of programming in a careful way in order to make sure that you get acknowledgments when you need them. Okay.
When you said the consumer pulls messages.
Right.
What's that action?
There's a call. There's a blocking call that you make
Right.
that doesn't return until the message gets pulled out of the queue. So the queue is typically there's a little tight loop that you're sitting in, and you just block waiting for a message. Okay, so everyone with me in terms of this basic kind of push-pull queue topology. So let's look at some pub-sub topologies. First of all, let's just talk about the routing system and how it works. Again, I'm going to have a producer and consumers. I won't bother to put the consumers up here, I'll just put the queues up. We'll have exchanges as usual, but now the exchange has to be put in not direct, but into the topic mode. The exchange is not in topic mode. It's just going to suck up everything that reaches it, which is not going to be useful. And then we have queues like we did before. Now, the difference between this situation and the previous situation is, on the sending side, there's no difference. But the route between the queue and the exchange now has to have a name. That's what's called the binding key. And binding keys can have explicit names. So for example, the binding key could have a name like, I don't know, my service. Right, and that's going to handle everything that's service one related. Now, if I, oops, what did I just do? Did he hit delete? Did I hit delete? No. Yeah. There goes the monitor. That's what I said, this is kind of flaky this out. Yeah, it's got to wind up. Let me just do this over. Producer, exchange. This particular exchange is a topic exchange. And we'll put a Q on it. All right, so if I look up this guy, look up this guy, I give this binding key a particular name. Now if I take a message here and put the routing key on it, service one, the routing keys and the binding keys match, so it goes along that path. Is everyone following? Now let's put another queue on it and another connection. And I'm going to call this one service one log. Now if I send the message service one, it does what I want. If I send the message service1.log, it's going to go down the log path, not down the service one path. But that's not actually quite what we want, right? Because we like, what we're logging is the service call. Is that everyone following what I'm saying? So what I need to do up here then is modify this binding key so that it will accept anything to the right of the dot. Actually, that's not going to be quite what I want. There's one more thing. And then I can take this logging service and I can set it up so that it can take 0 or more things to the left of the dot. So now my behavior is going to be a little bit more interesting. Right? I send something off to service1.log and it goes to both, which is what I want. Now, if I just send it to service one, though, it just gets sucked up because it doesn't match anything. So is everyone following what's happening here? So the basic idea then is that, let's do another one just so you can kind of see how this is all working. We'll make this one say star.service1.star. Right, so that's going to suck up anything that's got service one in between two other things. Right, so that would suck up, for example, service1.log messages. Right, it's going to the log stuff. It could have right, because now it's got 3 pieces. Is everyone with me here? So the difference here is that the hash mark is 0 or more. The star is 1, but it could be anything. Is that everyone understanding the differences here? Now this is effectively a pub sub system because the topic is defined by the name of the route. So we can set up pub sub then simply by being careful with the way that we're doing routes. Does that make sense to everyone? Now let's think about something like, say, the equivalent of an RPC call. So I want to make my RPC call across a well-defined system. So, and then I want to receive return value. So if you can think of this unit as both the sender of a message and the receiver of the response, that's this column. Is everyone following me? This column over here is going to be the receiver of the message and the sender of the response. Since you have to connect to queues, there has to be a queue over here to feed this consumer and a queue over here to feed that consumer. So I can feed this guy, he's going to feed this queue, he's going to feed this responder. We're going to get a response then, which is sent back, could be sent back to the same exchange. I'll look at how to get that working in a second. And then this can go down to this queue, which is then going to send a message off to this consumer. All right, so everyone following what I'm doing here? So what I want to have go along this path, this binding key, is my call, f.request. Is everyone looking here? The response here is going to go up to the exchange. And what I want to have going down this path is f.reply. So everyone understand what's happening here? And we can use the same exchange in both of those cases. So here I have the message, and I'll send off the request. Oops, this is not going to work. Well, it's not going to work because I didn't turn this into a topic exchange when I set it up, and whether it's arbitrary whether it's going to let me change it at this point. It might. Let me try. This is again the buggy software. Well, you can all imagine that. I'll say it, so I don't have to rebuild all this in front of us. I'll just point, right? So you send the request with the label f.request, and it's going to go along this path. It will produce a message with f.response, and it will go along this path because that's the only one where the things match. So is everyone with me so far? Now I could, at the risk of I'm going to risk making things seem complicated here. That I want to actually demonstrate something. So we've got another exchange over here.
But can we say actually effectively the two producer and consumer on the left-hand side actually can be the same process, the same right-hand side?
Yeah. All right, so what I'm going to do here is I'm going to just hook this guy up. Just pretend that one on top doesn't exist. All right, and we'll make this f.response. And then also we can go through this exchange up to this queue if I want to, right? So this now is f.request. So I'll make a producer here. Oh, I have a producer. I want a producer here that's going to feed into this exchange. So this producer, I hope this is not getting too complicated looking, has f.request, and it goes into the request queue and we're done, right? This one then, in terms of the return value, it would work pretty much the same way, right? Is that it would go into the same exchange, but now the exchange down to the receiver here is f.reply, right? So this routing key is going to be f.rep, and when we send it, oops, well, it ended up replying anyway. That's good. So here I can do f.reply, right? And away it goes. All right, now the thing that's interesting about this is that I can put an exchange down here, another exchange down here. And I can make this my logging exchange. Right, and it can take f dot 0 or more, actually, as it's indicated if I want to. So now if I send the reply here, for example, since it's still there, it goes to the log. And if I send the request here, and it's still there, it goes to the log. Is everyone seeing how this is working? So I can have an RPC system with logging on it, where everything is happening at the messaging level. And that's actually pretty handy. And by choosing the routing and by choosing the naming scheme, I can have very fine control over what I'm logging at any given moment. I could have a request log and a reply log that were different, for example. I could have a hash mark dot anything log, right? A hash dot hash log that would get every message in the system, just every message that went to a given exchange. So we can do a lot of monitoring then of the infrastructure itself, which is important. Is that, again, if you go into a microservice kind of world, once you're in microservices, you want to monitor the messaging infrastructure more than you want to monitor the actual services. Right? In other words, you can monitor the service to tell if it's loaded, but you could also monitor the number of messages that are given to the service to see if it's loaded. And that's actually more convenient. Because the thing that's doing the monitoring could be a service whose job is to spawn off other services on an as-needed basis. And that can all be done with the two services in question, not actually communicating with each other directly. So everyone understand the point that I'm trying to make here? I've got 3 microservices that are all running. I have a 4th one whose job is to spawn off more if necessary. Well, if this guy has to actually manage these 3, actually has to manage load on these 3, it's got to connect to all 3 of them. It's got to know that they exist. If on the other hand, if this thing is just managing the infrastructure, it doesn't need to know how many services exist or where they are or anything like that. Everything becomes much more flexible. So being able to manage things at the messaging level is I think, extremely important. Okay? Are there any questions about this stuff?
Just one question about airline choice of language. I mean, is that a risk if you wanted to use, for example, RabbitMQ?
Rabbit's pretty stable.
Commercial enterprise.
Rabbit is pretty stable, and it's used in a lot of commercial enterprises. So, I guess in theory, yes, but in practice, no. It is open source, so if you needed to modify it, you'd have to find somebody who do Erlang, right? Good luck on that, right? But it's pretty stable. But truth to tell, if you buy a messaging system from some big bucks vendor, you're not going to get access to that source code anyway. So it's kind of a non-issue. You're sort of at the mercy of whoever the vendor is, and Rabbit has a lot of users. And there have been most of its bugs, most of the serious bugs that I know about have been worked out. And there's a thriving ecosystem around it that you can use to ask questions and find out algorithms and that kind of stuff. So I think in practice it's not a big deal. Okay? Questions? All right, so that's routing.
One more question, sorry. Just because we didn't go through an example, does it support putting the message in one queue and only one consumer pick it up and process it?
Yes.
To basically provide load balancing in a way.
You can set things up so that the routing is from one exchange to one queue, no matter how complicated the routing is. When you set the queue up, you can prevent more than one connection at a time if you want to as part of the configuration. Right, but it's something you've got to be thinking about as part of the configuration. Now, Rabbit, unlike Zero, does support external configuration in the sense that you can specify the entire topology in a configuration file, bring up the broker, and it just builds it. So that's handy. In fact, if you are clustering, it's essential. Zero doesn't give you that option. It's that the topology is set up effectively by the programming system. So there's no way to launch without actually running programs that are setting things up. But on the other hand, you've got to run programs anyway. That's the whole point, right? It's having a broker without anything connected to it it's not a very valuable thing unless you're clustering. When you're clustering, you have to have brokers with nothing connected to it. But Zero is a simpler system, so it doesn't do that.
Are there guarantees for ordering messages in RabbitMQ? There
Well, it's always hard to guarantee ordering and messaging, because it depends on how long it takes to actually get between the physical nodes. So within limits, right, is that you can guarantee that things that go into a queue in a certain hour order are going to go out of the queue in the same order, right? But you can't guarantee the two things that are sent in a particular order will be put into the queue in the same order, because there might be a more complicated routing to wind up past through.
But once they actually ordered in a way in a queue, they will come out in the same order, won't they?
Once they're in the queue, yes. But a queue is a queue. It's not random. But what I'm trying to say is that the exchanges, though, are connected according to this very complicated topology. And you can have exchange-to-exchange connections also. And every one of those hops takes a couple of microseconds, and those microseconds build up after a while. So unless you can really predict the behavior of all of the exchanges and all the routing, you can't guarantee if they'll go into the queue in a particular way.
Can you have it so it doesn't actually queue?
No.
So basically, if you haven't got a consumer, it's just going to build a queue in the...
Consumers connect to queues. That's what they do. Consumers cannot connect to exchanges.
No, I mean, consumer connects to a queue,
Yeah.
but the queue's there and there's no consumers. Would that just fill up? It's like
The queue will just fill up, yeah.
Okay.
So even if it's set up as topics, it's effectively still queues. Is that correct?
Well, yeah, see, it's kind of confusing, right? Everything's routed. The better way to think of it is that topics and queues are actually both controlled by the routing strategy. Right, so when you're using Rabbit, what you think about is the routing strategy. You're thinking about exchanges, thinking, is this a fan out or is this a topic exchange? Because that'll control whether it's paying attention to the binding queue, or the binding key rather than the message. Or the routing key rather than the message. So see what I'm saying? In other words, if you put a routing key on a path, that's effectively a pub sub. If there aren't any routing keys, it's effectively a queue, because you don't know where it came from or where it's going to or you care. So it's all about routing. But you have to do that by selecting the right kind of exchange. So if you're doing queues, it's a fan-out exchange usually, or direct. If you're doing messaging, it has to be a topic queue. Because if it's not a topic queue, it will suck up everything. It won't pay any attention to any of the routing queue keys on the messages at all.
Is there an example for the limiting queue?
For
For the limiting queue, is there an example?
when you configure, you can do things like set up limiting on the queues and that sort of stuff. Yes. And the Rabbit has it's got an acknowledgement as part of the send operation. So if the queues fill, you'll get a known failure out of Rabbit, and it will immediately tell you that it can't queue it. You'll just have to sit on it then and decide what to do about it. But you can't, the message is not going to get lost in the sense that it will disappear into the broker and not come out again. It's that you'll know as a fact that it was not sendable with the queue as well. All right, is this making sense? So this is the hard part of Rabbit. Once you get this figured out, the rest is easy. Okay. Let me go back to the slides. So I don't want to spend a lot more time on Rabbit, but as I said, here are the pictures that we're just looking at. Here's another variant that we didn't have time for, but they're all there. I'm going through this very quickly, but there is a management console for Rabbit if you want to use it. We don't have anything like that on Zero. I just want to skip ahead just quickly to a little bit of code just so we can see what the code looks like. Good, thank you. So here's a little bit of just an example. Ruby, actually let's go to a language that you're more likely to know. Go to C#, for example. Right, so what's happening, I just want to show you just kind of in a general way what this kind of code looks like. You can create a connection factory to which you specify a location, right? Remember, you need to know how to connect. You need to buy. You connect to things that have addresses bound to them, so you need to know what that address is. You create a connection. You get a channel to that connection outside of the or to actually put things into. Here I'm declaring the queue in the code. So this is actually going to create a queue on the broker in the code. I could do that with a configuration file if I wanted to.
Will we own that queue? So when we go out and scope that queue?
No, it's in the broker. Right, because we have to have durability in the system. And if a system, if you could create a queue, put some stuff in it, and it crash, that would be a problem if the queue disappeared. And the system can't tell the difference between you crashing and you just shut it down. We put a message on it, we get it encoded properly, and then finally we publish it. Right, so this is kind of an annoying amount of work, but it's not rocket science. Okay, so everyone's seeing how this kind of stuff is. All right, good. So I'm going to now give up on the Rabbit slides for a bit and go to the ZeroMQ slides so that we can see the alternative. I apologize to the Zero people, by the way, for the way that they have represented the Zero with the Scandinavian letter. Is that if any of you are Danish or Swedish, I will apologize. Or I apologize for that. That's dumb. Right, to the idiots that did this, they said, "Oh, it looks like a zero to me." But so this is the way they're writing ZeroMQ now. You also see it written out as the words ZeroMQ, and you also see it as ZMQ, right? So it's up to you which way to do it. The website is zero spelled out, but this is the way that you see it in all the literature nowadays. So let's look at how ZeroMQ is put together. First of all, in terms of basics, the Z guide is an extensive, extremely well-written tutorial to everything that you need to know about ZeroMQ. I can't recommend it too highly. It's easy to read, and it's by far the best way to come up to speed on the system quickly. ZeroMQ itself is up on Git. You can just pull it down and just clone that URL, and you've got it. It's completely self-contained. It's got everything that it needs in there. It's also up on Homebrew, so if you're working on a Mac, you can just use Homebrew to download it to a Mac and get it installed and running. It's an easy system to put in place. It was built to do high-volume financial applications, which is to say it is actually rock-solid, reliable, and it's extremely fast. So you can do clustering if you want to roll your own cluster in ZeroMQ, but it can actually handle millions of messages a minute without any difficulty. So it's so lightweight and so fast that you don't really have to resort to things like clustering most of the time. Rabbit is much slower, so you're forced into clustering arrangements much more quickly than you would be in the zero environment. And then it runs on just about every operating system on the planet, including the mobile operating systems, which is nice, so that you can send messages from a phone into your messaging system directly without having to go through a server to do that. And it supports every language you've ever heard of and some that you haven't. I have no idea what Luke is. I would love to know what Luke is, but I have no idea what Luke is. But ZeroMQ supports it for what that's worth. I hope it's in a language, but it might not be. The zero business is that, well, all of these zeros that I've listed here. And for the most part, that's true. There is almost close to zero latency. It's very, very fast. There's no administration overhead because it's so simple that you don't really need an administration console or anything like that to get it running. It doesn't cost anything. It's free. And zero waste in many ways, but it's zero waste in the sense that it does exactly what it needs to do and nothing more, but that's a good thing. It's nice that is a good thing. Now, the basic conceptual unit of ZeroMQ from a programming point of view is the notion of a socket, which will hopefully be more standardized than this kind of socket, since these don't look like your kinds of sockets. But the basic idea is a socket. But it's not really your grandfather's socket in the sense that it's, when they use the word socket, if you've been programming in the Linux or anything except the Microsoft world, now even the Microsoft world to some extent, you have this picture in your head of what a socket is. This is not that, right? It's a socket only in the sense that there's an elaborate network on the other side of it that you don't know about. What it really is a port. It's a portal into a messaging subsystem that is built for you, that does all the hard work. So in Rabbit, you've got to worry about things like topology, and you've got to worry about loading, and you've got all this junk you've got to worry about, the system admin stuff. That's all on the other side of the socket. All that we care about is stuff that's on our side of the socket. So I'm going to use the word socket because that's what the literature uses, but this is not sockets in the standard Linux sense of the word socket. Right? It's a much more sophisticated thing. For one thing, you combine multiple addresses to a socket if you want to. That's a huge difference between that and the standard Linux socket. It's asynchronous in the sense that the underlying queuing system is multi-threaded and extremely fast and asynchronous. Now, the socket itself is not. The socket itself is single-threaded. It's a huge mistake to try and pass a socket between two threads. It's almost impossible to synchronize in such a way that that's going to work. But that's fine because it is a multi-threaded system. It's just that all of the threading stuff is done for you on the other side of the socket. And if two threads each have their own socket, that's not a big deal. There's not a lot of overhead here because, again, the system on the other side of the socket will take care of eliminating any duplication. So the socket is used by a single thread, but on the other side it is multiple thread. It supports multiple endpoints in the sense that a socket can bind to multiple addresses, and a socket can connect to multiple addresses. You can use lots of transport protocols here. We'll look at all of them in a moment, but pretty much anything you want as a transport protocol is available. It handles all the threading. It automatically handles the issue of a machine going down and back up again. So your program just doesn't have to worry about it. If it crashes and you bring it back up, it just works. It doesn't matter what order you create things. You can create the server side before you create the client side or not. It just doesn't care. And again, these are very hard problems. I am happy to have them be solved for me. Transport protocols, these are the ones that are available off the shelf. You can add your own if you want. Inproc is communicating to another socket that's inside the same process as yours. TCP is TCP. TIPC is a named pipe protocol. That may or may not be supported depending on the operating environment you're in. It didn't used to be supported in Windows, and it has been for the last couple of years. So, but depending on which version of Windows you're running on, you may or may not have the equivalent of a named pipe. It's always been supported in Linux from day one. Fortunately, it's not a big deal because if you go through TCP, there's not much of a loss there, even if you're on a Windows system. So generally, I don't think there's much point in going through a named pipe protocol, but you could just use TCP and do that in a flexible, platform-independent way without having to care about what operating environment you're in. PGM, there are a couple of, in other words, fancy multicast versus unicast sockets and that kind of stuff. But really, the main things you're going to be using here are inproc and TCP. Those are the two main ones. Right? Inproc is extremely efficient when you're inside the process. You can get security if you want to. The security is an end-to-end security inside the messaging system itself. So Rabbit gives you security only in the sense that the connections to the server, to the broker, can be SSH images. I haven't really gotten into it yet, TLS connections. But that's not really security, because once you get into the data center, it's not secure anymore. Zero supports end-to-end security from the production to the consumption of the message. So the message itself is encrypted using an elliptic curve algorithm. So if you need security, you get real security, but you have to install another package that runs in parallel. The URL for it. Just go to the curvezmq.org site and you can download it. All right? Now, let's look at some of the ways that it's used, starting with the simplest possible way. You have a client, you have a server, and you have two or more sockets in one. Let's start by just looking at this path. So the basic idea is that you open up a request socket. In other words, sockets are tagged or organized into types. A socket is not a generic thing. So a request socket is something that's different than a reply socket. We'll look at the code in a second. The way that the request reply sockets work is they overlay and mandate a request reply protocol. So if you're using a request socket and a reply socket, you must use it in the way that those sockets are designed to be used. And in the case of this one case, this is not the case in other protocols, it's stateful. So basically you make a request on the request socket, that sends the message to the reply socket. The reply socket does whatever work you're asking it to do. It replies to the same socket, reads from the socket, then writes to the socket. That sends the reply back up to the request, which then reads it. If you don't do all 4 of those steps, you're hosed. It's a stateful situation. Now, we're not going to have time here to talk about how to deal with that. There's an entire chapter in the Z Guide that talks about how to deal with the problem of the entire handshake not happening. But, and fortunately, there are other topologies that we can use that don't have that statefulness to them, so it won't cause that problem. But it's pretty convenient to be able to do this sort of thing, because basically what we're making is a remote procedure call where we get a return back. All right, it's like it is a queue. There are queues underneath all of this. So you can have multiple requests queued up. In this particular picture, I've put a second server onto the client. Right, in the sense that if the request is sent out, essentially you can have multiple handlers of the request, let's put it that way. And it will round robin between them. So you send a request out, another thread inside the same application can send out a second request while the first thread is waiting for a response. And the socket system will keep track of all of the IDs and stuff that it needs to get that all sorted out in terms of getting the correct response hooked up to the correct request. All right? Now let's look at how this is implemented, because this is really at the heart of how ZeroMQ works. Use the code. It's extremely straightforward. This is Java. I put all the examples of Java. The C# client is actually a little simpler still. So in the Java implementation, with all implementations, you have to start out by creating something called a context, which is the creator of all sockets. In the Java implementation, you ask the context for a socket of type request. The C# implementation is a little bit nicer. So in the C# implementation, you say context.request. And you don't have to worry about the extra enum over here that defines what kind of socket. So that's a little bit cleaner, but it's basically the same thing. And then you connect. And in this case, I am the client, so I am going to connect to a specific address. Somebody who's going to serve my request. Is everyone following me here? So that address is typically going to be pulled out of the configuration file someplace. You need the whole thing, including the port number. Then I'm going to send some requests. So I'm going to send out 10 of them. And I create a request. In this case, it's just a string. Right? Hello 0, hello 1, hello 2, hello 3, and so forth. And I say to the requester socket, send this request. And it has to be sent as an array of bytes. In Java, everything is in Unicode, so we have to call get bytes to turn into bytes for us. Is everyone with me here? Then we have to wait for the reply. With the request response, we have no choice. So I wait for the reply to come back, and I'm done. That's it. So compared to Rabbit, this is trivial. This is so easy to use that, as some people say, I learned Rabbit and I went out trying to figure out applications that I could write in it just because I wanted to write something in it. It was so cool. Because this is very simple. The more you've dealt with messaging systems, the more you appreciate this simplicity. Right? The other side of this, the serving a request, is equally simple and instruction in almost an identical way. I create a context. I get a socket. In this case, it's a reply socket. Now, on this side, I'm binding. Right, on the client side, I can have multiple clients hooked up to my server. So the clients connect. There's a single server that's going to be handling multiple requests. So it binds. Everybody has to know the server's address. Right, so everyone with me here? Now, and notice that it's just binding as a port number on any machine, which is kind of handy if you want to make your topology based on port numbers rather than on a combination of port numbers and IP addresses. So with the star is going to pull the IP address of the current machine off the system logs and And now I'm going to hit this loop where I'm handling the requests as they come in. So there's a receive call. I'm printing it. I'm sleeping for a second or so just to pretend that I'm working. A lot of people sleep while pretending that they're working. And then I post a reply back. And again, this is trivial. This is easy to do.
Send and receive is all in bytes. Yeah.
It's all bytes, everything's bytes. But as soon as you go drop into messaging systems, it's always bytes.
How long can the client wait?
Forever. That's the problem. And as I said there, I don't want to get into it here because it's too much detail, but there's a whole chapter in the Z guide that talks about exactly that problem. So it's a solvable problem, but you have to solve it. More to the point, request reply is kind of it's the simplest of them, but it's also the least capable of them. At least, you don't use it very much.
Any possibilities for asynchronous receiving?
So what?
Asynchronous receiving.
Well, everything is asynchronous here.
But we enter waits for.
Oh, and this is not asynchronous, but there is. Bear with me for a moment. I'll give you an example. All right, let's look at the pub sub architecture. Here we have a single publisher. We have multiple subscribers. The subscribers are all hooked up to the same publisher, obviously. The publisher binds, which is to say the publisher has a fixed address. The subscribers connect to the publisher. Again, we can put a broker in the middle if we want to, but in a small system, there's no point. So the publisher doesn't know who connects to it. When it publishes, everybody who has connected to it will get the message. Okay? All right, let's look at code. This is structured almost identically to the code that we were just looking at. Create a context, create a socket. This time it's a publishing socket. Bind to a particular address. Now, I did this just to demonstrate that you can. Notice that I have bound to 2 different addresses with 2 different protocols. So what that means is that my clients can connect to me at either address using either protocol. And when I publish, it'll go to all of them. And that's pretty handy. And then I hit a publication loop where I am just floating around here forever inside this loop, or at least until I'm interrupted. And I am pretending to work for a while, and I'm creating a message, and I'm publishing it. And again, that's all there is to it. This is all happening asynchronously. It's all properly queued. It's all robust in the sense that if the server goes down and then comes back up again, everything will be fine. We just don't have to worry about it. Right? It'll be fine in the sense that everybody who was connected, fine in the sense, and this is an important sense, that everybody who was connected to me when I went down will be reconnected to me when I come back up again. And I don't have to do anything to make that work.
Would you get notifications when the other side is down?
You don't need a notification.
No, you don't
it just happens.
You don't know who's the other
You
side.
don't care.
Yeah. Silly question.
Yeah. Let's look at the subscribe side. Create. This should be familiar by now, right? We create a context, we create a socket. This is a subscription socket. I bind to one of those 2 ports. Now notice that this time I'm binding to 5556 on the local host. In the previous code it was *:5556, and that's fine, right? Star matches everything. And then I subscribe to the message. That's the one new step here, is I have to subscribe to the message. Now, we didn't see any messages on the other side though, so what's that about? And the answer is, notice I'm subscribing to a message ID. If I go back to the previous slide here, if I go back to the previous slide. Notice that message ID is just the prefix string on the outgoing message. Now, we can be more sophisticated than this. Is that Zero does have some mechanisms to build up a multi-part message where we specify the message, the topic, with a separate call. And we can build up the message as kind of a little packet that's got a separate topic from the message body itself. But in the simplest case, we don't have to. Everything just kind of works. So the initial few characters in the outgoing string is the topic. And when we go to the subscribe side, all that we have to do is specify that string, and that's the topic. We subscribe to that. And any message that's got this prefix is an incoming message. Is that everyone with me here? And when we receive it, it will be stripped off for us. So what this string is going to contain is everything except the first whatever many characters on the incoming string. So again, this is trivial stuff to do. Now let's make things a little bit more complicated again. Is here what I want to do is divide and conquer kind of application. Is that I want to take an operation and I want to break it up into 3 workers. I want them to work on it in parallel, and then I want them to publish the results to what's called a sync, which is going to put them all together. Right? This is Google in a nutshell. Right? So the basic idea then, though, is we're using a different kind of socket now. Now, push-pull sockets are kind of like request-response, except they don't have that handshake built into them. They're just simple queues. So you push, oops, excuse me. I'm going to have to draw the whole stupid thing again, sorry. But anyway, you push to a queue. When you push your message to a queue, and it sits there forever until somebody else pulls the message off the queue. So there's no need to pull things off. There's no requirement that you publish a response before you can get the next thing. There's no requirement that you get the response before you push the next thing. It's just a simple NQ, DQ kind of situation. So it's much more flexible. So I'm going to push to these tasks, who are then going to pull the request. They'll do whatever work they need to do, and then they'll push the result down to the sync, who will pull the results in. Now I'm going to mix a little pub sub into this, right? Because how do you know when the response is available? So what it does is just then publish a topic that says I'm done, which the ventilator up here is subscribed to. So the ventilator pushes everything out and then sits in blocks on the subsocket waiting for something to appear there. All right, this is an architecture I'm going to come back to in a second, and if you're going to take my microservice session tomorrow, I'll talk about it even more there. It's an important architecture. Okay? So let's look at some code. Here's the ventilator. So I've split things up into colors so that we can see which piece is doing what. I'm starting off by defining a socket that I'm going to use to push to however many workers are connected to me. I don't know how many workers are going to connect. I'm binding, right? The ventilator binds. So there could be any number of workers connected here. I don't know how many. I then need to create a socket that I can use to get information back from the sync. Is everyone following me here? And I need to talk to the sync. I have two things. Now, I need to talk directly to the sync because I need to tell it, I'm about to start a bunch of activity. Initialize yourself. Is everyone following what I'm saying? So I'm pushing to the sync. And then I am making a subscription socket so the sync can tell me when it's finished. And in this case, the topic is done. Is everyone with me so far? Now the next issue is it then waits. And this is, again, something it's talked about in depth in the Z guide, so I'll just refer you there, but just let me explain the problem. You cannot control how long it takes for a socket to come into existence. And as a consequence, it's very difficult to handle startup situations in this kind of environment. Because the sockets and the clients and the servers can be coming into existence in random orders, and you can end up in a situation where none of the messages get sent out to anybody if you're not careful. So what this is doing is it's handling that in the stupidest possible way. It's saying, when all of the workers are running, tell me. Now, of course, you can do that using messaging also. But in this case, it would just clutter up the example. All right, so I say to the sync, I'm just sending out the number 0. That says initialize yourself. So I've told the sync to initialize itself. I go in a thread and I spawn off 100 units of work. Now if there's 100 workers, I'm going to now have 100 workers working in parallel. If there's 50 workers, I'll have 50 working in parallel, and then as they finish up, they will gradually suck up additional units of work to do until all of the work is done. So I don't know or care how many workers there are. I just spin them out to as many workers as there are. And then I sit around waiting for the reply to come back. Waiting for the message to be published to the purple pub sub channel. So is everyone seeing how this is working? And then close it.
But all workers get all messages.
Hmm?
Is it fair to say all workers don't get all messages?
Yeah. All right, now let's look at the worker. The worker has two sockets. It has a socket to pull work and a socket to push to the sink. The worker does nothing but connect, which is a good thing because we want to have an arbitrary number of workers. If there were any binds in here, we couldn't have an arbitrary number because that would mean somebody would have to know our address and be connecting to us. So everything's a connection. Everything's a connection. So we connect to the ventilator that we're pulling from, we connect to the sink that we're throwing to, and then we grab some work to do the work, however we would do that, and then push the result down to the sink. The sink itself is equally trivial. We create a socket to pull things out of, we create a publication socket to publish the done status. We sit in a loop and we pull the results in as they come. And then we send a done flag up to the initial. John, I've noticed that I'm passing the result as part of that message. So again, this is really, really clean. You wouldn't even know that we were using a messaging system here. But underneath this is this nice, reliable, queued messaging system. All right? Is this making sense to me? Now, we can build proxies if we want to. Here's an example of a relatively simple proxy system. In other words, if we need something that's broker-like, there's nothing stopping us from manufacturing a broker. There's a unique protocol, though, that needs to be used for this because there's routing information that has to be managed that a standard pub and subsocket doesn't manage. The thing that's important here, in other words, is that xsub knows that when I publish using xsub, it knows where things are going so it can route stuff properly. Right? So the proxy has an xsub and an xpub. It's going to read from xsub and write to xpub and do hardly anything else. And in fact, I don't remember if I put the code in here for this, but the code, you can write this code, this loop yourself, but it's happened so often that there's actually just a function code that you can make this. This is a one-line proxy. And the important thing here is that the binding is all happening in the proxy, and everybody out here is connected. So I can have any number of publishers publishing to any number of subscribers through this proxy. And that's, again, pretty handy. Now, you have to build this, though, right? This is a 10-line program, but it is a 10-line program, right? You have to compile it, you've got to launch it somehow. It's got to be on a machine someplace with a known address, right? If you're going to put it on a separate computer, you've got to like spawn off a EC2 virtual machine and get the proxy running on it. But it's not much work to do that. We're talking about 10 minutes literally to build the whole system. So we can put brokers in here, in other words. If we want a broker in order to get the, it's really handy to have any number of things connecting to any number of things without having any bound addresses here. So if we need that, we can build it. If we went point to point, that works just as well. It's just as easy. All right, the other architecture I want to show you is, and again, we'll come back to this if you're going to be in my microservice classes. My original thought about the microservice class was that I was going to spend the whole time looking at code. And I started putting that class together, and it actually wasn't very interesting. It was just a bunch of boring looking code. So I kind of turned it into a practical microservice architecture class, where I'm going to be talking about practical implementation of a specific service that I wrote, rather than Neil's pie-in-the-sky 3,000-foot view that he gave of microservices yesterday, which has its own value, but it's a different take. But this is central to the notion of getting microservice to work, this architecture, so it's really important. What we have here is the problem of how do you build a web front end to a service architecture. Now here, the turquoise squares are services. They're microservices. And the gray squares have one job. They are translating HTTP into a service bus request. So what happens here is this thing is doing one job only. It's sitting at port 80, gets an HTTP request. It takes all of the data, sticks it into JSON, and pushes it into this broker. And you can have as many instances of servers here pulling from the broker as you want. So everyone follow what I'm doing here. The broker does the work, it publishes the result to a pub sub broker, who then gets it back to my original HTTP proxy, which then turns it into an HTTP reply and sends it back out. Now that's probably enough to handle most of your web traffic. If you needed two servers though, you just spawn off a second one and it pushes to the same bus. Now, there's going to be a little bit of hardware load balancing here that I'm not showing. But this is a spectacularly useful architecture. Now, this web piece, fortunately, has already been built for us. There is a program here called Mongo 2. Many of you were programmed in Ruby. Mongo was Ruby's server. And the Mongo 2 project is basically, it uses the HTTP engine from the original Mongo. The rest of it is a ground-up rebuild. And what it is a web server that does two things. It will serve static pages, and it will translate HTTP posts into service bus requests on ZeroMQ. So the way that you build a web application using Mongo is not with things like servlets and all of the junk that you do with IIS. What you do is build a bunch of little ZeroMQ aware services. And they just connect them to the right buses, and away you go. Configuration for this thing is just trivial. It's a file that says, when something comes in at this URL, post it to this IP address and port. And that's all that that's 100% of the configuration. And you launch it by just launching it. It's a very tiny little program, you just run it. This thing is about 3 orders of magnitude faster than IIS. So if you go to a messaging-based system, this kind of architecture is really, really handy. Okay? So there are a couple of issues. There's no durability. There are no brokers, which is either a good thing or a bad thing, but how you want to look at it. It's not thread safe in the sense that you can't pass sockets between threads, but that's not too big a deal. Because you can open up sockets on two threads. You just can't pass them around between threads. Only certain combinations of sockets work, right? Pub and sub work together, obviously, request and reply, and so on and so forth. If you try and do any other combination, it just won't work. But that's pretty much the only downside. This is not a big deal.
What language is available? Zero, what language is available?
What languages are available? Anything you can imagine.
Oh no, what is it itself?
Oh, what is itself written in? It's written in C.
C.
All right, any other questions? We've reached the end of our time, and I have reached the last slide at almost exactly the same time for a change. What a concept.
Going back to Rabbit, sorry, going back to RabbitMQ for a second. Let's just say you're doing technology selection. Let's say you're working in a distributed environment, you've got quite small messages, and you're not doing pub sub, you're just doing full bunch. Obviously, MSQ is one of the choices available to you.
Yeah, it is, and it's okay. You know, I probably wouldn't go to the Azure bus, right? There's too much overhead and stuff associated with the whole Azure messaging thing. But MSQ is a reasonably good system. The main thing I have against most of the Microsoft technology is the lock-in problem. So if you know as a fact that you're going to be in the Microsoft ecosystem forever, we'll go with it. Right? But it's perfectly good stuff to work with. On the other hand, more and more people that I know that are working in the .NET world are incorporating open source stuff into their programs. And I know many .NET applications that use Rabbit and Zero, both of those. So there's no compatibility issues between the two.
Do you think that's more as a future-proofing and a sort of individual sort of benefit they're getting from?
Well, you know, I'm not the right person to ask because I live in the San Francisco Bay Area and things are just weird there, right? It's like this giant experimental thing. Right? And we who live in the Bay Area think that we're technologically superior. We're wrong, but that's what we think, right? whole world is behind us by 10 years, right? But the fact is that we're this giant experimental test bed and 90% of those experiments fail. So in the Bay Area, at least, the biggest programming language right now is Ruby. And JVM languages of one sort, right? Is that Twitter just rewrote its entire infrastructure in Scala. And so most of the projects are open source. I know of no .NET projects happening in the Bay Area, except .NET projects in big corporations that are so invested in .NET that they can't change course. But I don't know a single new project by a new company that's being done in .NET in the Bay Area, not one. But then you come over here, right? And the whole world has flipped over. Everything's .NET, right? Hardly anybody's using the open source stuff. So in the Bay Area, people are using Zero just because that's the obvious thing to do. Nobody's on .NET. Zero is really easy to program. It's adequate for almost all of the applications, and it's very, very good. So it's not really a future-proof thing. It's a now-proofing thing, right? Is you want to hire somebody, the odds are they're going to know Zero, right? But in different places, it's different, right? This is all very geographic. It's the technology that is most dominant changes from place to place. Certainly as you move around the U.S., and certainly the differences between Europe and the U.S. And I haven't done any work in the Middle East or somewhere like that, but I imagine it's different out there. So it's just kind of what people know and what the employment pool looks like, right? It's who can you hire and what skills do they have. Technologically, I don't think there's much difference. The only thing I would think in terms of future proofing is that Microsoft and Apple are changing roles as we speak. Microsoft is becoming more open and Apple is becoming more closed. So in terms of openness then, it seems to me that starting to incorporate some open source stuff into the .NET world is probably a good thing, as Microsoft is moving in that direction anyway. But I don't know, I can't predict the future. I don't work for Microsoft, so I have no idea what they're doing. Okay? So thank you very much. 9% of the synchronization problems associated with multiple threads. And it does it in a way that's very simple to code. So messaging is actually a great solution in process for situations where you're going to have multiple threads, and particularly if you're doing background processing. It's good for distributed development because the message handlers could be anywhere. In the case of ZeroMQ, they can be in process, they can be on the same machine but in a different process, they can be on a different machine. You don't care. So what that means is that you can test all on one machine, you can develop all on one machine, but when it comes time to deploy, you distribute your application just by copying things to different machines, and you tweak the addresses. The TCP addresses, instead of being localhost, become something else, and that's the only change you have to make, and everything continues to work. So it's really easy to do development in this kind of environment. It supports polyglot applications in the sense that you can write all of your services in different languages if you want to. They don't care, as long as you're passing things around as JSON rather than as binary. So, and you want to do that, really. It's in the microservice world, it's kind of encouraged within limits. Right? You don't want to use every language you can possibly think of, but there are a lot of systems I know of that are part PHP, and they're part Scala, and they're part Java, and they're part C#, and that works just fine. So because of that, you can get real independence between the modules because they don't have to be tied to each other through any dependency except to the messaging system. And that's obviously a good thing from a maintenance point of view. They're also messaging is a great way to share information. Because a lot of times, if you see old applications, people would share information through the database. One server would write to the database, another would read. You'd store session information in the database, for example. Messaging is a much better way to do that, to pass that information around. Database is very inefficient, and it's another single point of failure. So it makes development go faster, it improves the flexibility of the system. It makes it easier to develop, right, is that your development goes faster. It's really cool. Rabbit itself is an open source system, which is not, it's written in Erlang, which is kind of a weird choice. So Erlang is one of those languages that nobody is interested in outside of the academic community. Erlang is a purely functional programming language. Erlang has exactly one reasonable application to write in the language, and that's a messaging system. So the fact that in other words, Erlang, the one thing that a pure functional programming language gives you is thread safety. It makes it really easy to write heavily multi-threaded applications without having to worry about all of the problems that we usually ascribe to that. Messaging brokers are very heavily multi-threaded. So Erlang is actually a pretty good choice, except there's nobody in the world who understands it except the people that work on Rabbit. So practically speaking, the only downside is that we have to install the Erlang VM in order to run Rabbit, but that's done automatically when you install Rabbit, so it's not a big deal. It's polyglot in the sense that there are a gazillion bindings into Rabbit. Just about any language that you can imagine can talk to Rabbit, from JavaScript to C#. And it does use a standard protocol. It's built on AMQP. We'll talk about that in a second. There it is. So AMQP is a binary wire protocol. It's very efficient. It was created by people who were actually doing messaging. But I'll say that as an aside here, it's people in the enterprise doing messaging. So it's kind of geared towards enterprise applications. It is interoperable, it's scalable, all of this usual goodness and light stuff. Oops. The one thing I will say about AMQP that I don't like, though, is that AMQP is built on a notion of guaranteeing as much as possible. The enterprise guys are really into guarantees. And AMQP allows for two very hard things. It allows for durability, which is to say that the message will continue to exist even if servers in the system crash while the message is progressing through the system. And it allows for guaranteed delivery in the sense that once a message is put onto the system, you are guaranteed that it will be delivered to somebody at the other end eventually. Now, those things are extremely hard to get right. In fact, I would argue that nobody has got guaranteed delivery to the point where it's actually guaranteed. There is no way to guarantee that every combination of servers crashing at inopportune times is going to be recoverable. It's just not going to happen. It's a dream. So there's a lot of complexity in AMQP that has to do with these guarantees. And it turns out that you don't need those guarantees for the vast majority of applications that use messaging. And so Zero, at the other extreme, gives you none of them. The only guarantee that Zero gives you is if you send a message in multiple parts, you'll either get all of the parts or none of them. Guarantees atomicity. But it doesn't guarantee anything about the message arriving. So if that's important, you have to do something in the code to make sure that it's arrived. You have to acknowledge the fact that you've received the message, which is not a big deal, to be honest. And it simplifies the messaging protocol so much that it's really worth, I think, a little bit of extra effort on the part of the program. Now, there are a couple of metaphors with respect to messaging that work across all systems, again, whether or not there's a broker present. So let's talk about them. First metaphor is the publish-subscribe metaphor, which we're all familiar with at some level. The basic idea is that you have a publisher who publishes things on a certain topic. And when the publisher publishes that thing on the topic, the publisher talks to the broker, but nobody else. The broker talks to the subscribers. But notice that only two of those guys got a newspaper down there. In other words, if you don't subscribe to the topic, you don't get the message. So the basic idea of publish-subscribe is that only people interested in certain topics get messages. And it's up to the subscriber to express its interest in the topic in order to be informed when something is published to that topic. Now, there's usually wildcard mechanisms here. So, for example, there might be a logging subtopic. You might have a service topic with a logging subtopic. And all of the services would subscribe to the service topic. But then a logger might subscribe to the service's logging topic. Now, does everyone see what I'm saying? But there might be a logger that subscribes to the equivalent of star.log. I want to hear logging for every service, regardless of what it is. Right? So there's a certain amount of wildcardness that's useful with respect to defining how the topics work. But this is a topic-based system. This is based on, the publisher doesn't know how many subscribers there are. The subscribers don't really know who the publisher is. The publisher could tell him. You could put into your payload some kind of return address or some sort of indication about who's doing the publishing. They're generally written in various languages. They could be written in varying operating environments. They could be running on different operating systems, running on different machines. And if you start sending binary data around, it's a world of hurt. Is that you don't know whether it's big endian or little endian or you know, what's the precision, et cetera, et cetera, et cetera. JSON is completely implementation and context independent. It's all asking. It also has the advantage of being human readable, so it's easy to log, it's easy to see what's going on inside the system as it moves around. So more and more I've been avoiding having binary payloads. It's just isn't worth it. If you were sending massive amounts of data around, I don't know that messaging is the best way to do that anyway. Right? In other words, that's where you would fall back onto a binary payload. But to be honest, I think you'd be better off putting that massive amount of data in some other place and sending its address around and sending the data around in that kind of situation. So generally speaking, the payload is going to be text. It's going to be something that's human readable. None of these systems, though, require that. The payload can be any string of bytes you decide to send. I should also say string of bytes is that all of the messaging systems are ASCII. They don't mess with Unicode. Because Unicode is another world of hurt. It's just too hard to interpret. So UTF-8 and yada, 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 anytime there's a string in a messaging system, it is an ASCII string, 8 bits per character. So again, the payload is arbitrary. So if you want to send encoded Unicode across this payload, go for it. Right? But in terms of the messages themselves, I would recommend avoiding that. It's just stick to ASCII. Now, the message then travels from the producer to consumers. In the case of Rabbit, through a broker. In the case of ZeroMQ, which we'll get into a minute, not. Zero is a brokerless system. Rabbit is a broker-based system. Now, by broker, I mean it is actually a server, not just in the sense of a program, but also in the sense of a machine, usually. Now, for testing purposes, it doesn't have to, because the broker could be running on this. The broker service could be running on the same machine as the code that you're building and testing. But in practice, the broker is going to be one or more machines living in a cluster in a data center someplace. So everything in Rabbit is done through the broker, so let's start there. Now, there are a couple of advantages to a broker architecture. One of them is that the brokers, since they are running on their own machines, can be maintained by a bunch of professionals whose job it is to maintain stuff. In other words, they can go inside a data center where there are people whose job it is to keep them live. The second issue with the broker is it's replicable in the sense that you can have a cluster of brokers. So you can have a cluster of several machines that act as a single broker. Now, the downside of that, as compared to a point-to-point kind of system, though, is that it is a single point of failure, either physically or logically, inside the system. So in most small messaging setups, the broker is just one service running on one machine, and if that machine goes down, you're host. And implementing a clustered environment is possible, but it's hard. Is that it's somebody's got to study to do it. They've got to be certified as an engineer that knows how to do this kind of stuff. And it's not something you want to do unless you have an enterprise requirement to do that. So brokers then are kind of a mixed bag. The third thing about brokering that I'll talk about a little bit more when we get to the ZeroMQ part of the talk is addressing. Now, if you think about it, the broker is a machine by itself. So these two connections on the two sides of it have to have well-known addresses, TCP addresses at well-known ports. These guys don't, because these guys connect to the broker from the outside. And as many people as possible can connect, as many services or producers and consumers as possible can connect. And nobody needs to know what their addresses are. And that's actually a good thing. Right, so the basic concept is this is called a bind and this is called a connect, right? And you bind to a specific physical address. And then you can connect to that address. Ideally, in any kind of messaging topology, you want to have as few binds as possible, because that makes things inflexible when you have binds. You have to know what the address of it is in order to bind to it. It's better to have connects. So brokering systems, at least messaging systems where you have a thing in the middle, is helpful because it concentrates all of the known physical addresses in one place. And the vast majority of the system doesn't have to be at known addresses, which makes it much more flexible. Is everyone following what I'm saying here? In other words, if the consumer were a service, and I wanted to put a new service on it, I can put the new service on and it can just connect to the broker. And the producer doesn't need to know that I put a new service on because it doesn't need to know its address. Right? If the service was bound to an address, I'm in deep trouble because now every time I put on a new server, I have to somehow tell that to the producer, who then is going to have to physically bind to it, and that's not really a good situation. You want to use messaging for a bunch of reasons. It's easy to put new requirements in the system because the handlers of the messages can be added very easily without impacting existing handlers. So in the microservice world, for example, where you're talking about a microservice that's doing exactly one thing, you bring a new service online that didn't used to exist before, the existing services don't even know that that's happened, they don't care. So when a new requirement comes along that needs new services in order to implement that requirement, you can just put the new service in place and you don't have to touch any of the existing code. It's painless with respect to scalability, and you can scale hot in the sense that I can throw more servers onto this system and nobody cares. It's just suddenly the load is distributed between multiple servers when before it was not. Well-done messaging systems require almost no load balancing. Is that the messaging itself does the load balancing for you. You can put new services online without having to bring down anything, and that's a good thing. It's easy to do background processing using messaging, and it's, in fact, Zero, not so much Rabbit because it's a little higher overhead, but Zero is very, very low overhead to use in an in-process kind of situation. So a service that's handling messages in ZeroMQ could actually be an object inside your program that's using messaging to talk to other objects inside the program. Now, the advantage of that is that there are a whole bunch of asynchronous design patterns built around messaging, which are vastly easier to keep track of than messing around with semaphores and stuff. Because nobody understands how low-level thread safety works. Nobody does. And if I do, but let's say that probably 5% of the people that use threading actually understand what the hell they're doing. And the stuff breaks all the time. If you go to a message-based strategy for multiple threading, where you have several services running on independent threads, talking to each other across a messaging bus, that solves 99%. Now that everyone's had a big carbohydrate-laden lunch, which will guarantee you will fall asleep in about 20 minutes, we can leap into a complicated topic that would be hard to follow. Actually, it won't be that. What this talk is messaging. I'm going to look at two different messaging systems. I'm going to look at Rabbit and I'm going to look at Zero. The two of them are, sometimes you use one, sometimes you use the other. Neither is clearly better. Which is to say, it depends on the context. I'll talk about AMQP in a minute, but Rabbit is based on it's based on a protocol called AMQP that's widely supported by enterprise-level messaging systems. So what that means is that if you need to integrate into an enterprise-level messaging system, Rabbit is your choice. ZeroMQ is based on nothing. It's its own thing. On the other hand, ZeroMQ is much easier to use than any AMQP messaging system. So ZeroMQ is your choice if you are building an entire system of your own that doesn't have to integrate with anything in particular, and you want the simplest possible programming model. So as to neither one is appropriate or inappropriate, you could use them interchangeably in the sense that if all that you're doing is messaging internally inside your own app, it doesn't matter which one you use. But when you have to go to an outside app, you have to go to an enterprise messaging system, Rabbit is your only choice. And if you know as a fact that you're never going to have to go to an enterprise messaging system, I would go with Zero because it's easier to program. So those are that's why we need to talk about both of those, that both of them have their applications. On the other hand, they're both messaging systems, which is to say there's a lot of commonality between them and certainly a lot of common architecture between them and common concepts. So I'm going to start by talking about conceptual things. I should also say I've got these slides up on my website right now. They'll also be on the conference website, but I've just uploaded them this morning, so there's a fresh version up on my website. You can go to the slides directory. The one thing that you won't see, but I'll get you where I'll for it is there's a little demo of what everything is, and you get a link to that on the URL. So let's talk about messaging for a minute. The concept of the notion of messaging is that you are sending payload across the wire between a producer and a consumer. So we have a message. The message has in it a payload of some sort. Now, what that payload is pretty much arbitrary. Is that it could be binary, it could be big, it could be small, it could be text, it could be JSON. If you're going to work in a microservice environment, which is where I'm using messaging most heavily nowadays, my payload is always JSON. It's always human readable ASCII. And the reason for that is that in a microservice environment, but this is the case in almost any environment where you'll see messaging, the consumers, the things that are handling the messages, are in a sense an unknown quantity. And in a microservice world, each service will be a consumer, and the servers could be